This is Official Nerd Business. Hello nerd boys and girls, and welcome back to our programming series. Today we will be taking a look at Euler problem number 27, and we will be using Python 3 in order to code our solution. So let's have a look. I have it on the screen here. This is a screen capture from the Project Euler website. I think there's a lot of details in the way they formulate this that are lost when we copy and paste this as plain text, so that's why we have this in image form, and there's a lot to take in here. We are looking at quadratic primes. Euler discovered a remarkable formula for n squared plus n plus 41, and it is a remarkable formula because it turns out that the formula will produce 40 primes for consecutive integer values of 0 to 39 for n. However, when n reaches 40, 40 squared plus 40 plus 41 is divisible by 41, and as we can clearly see, if we set n to be 41, so when we set n to be the equal to the integer coefficient, then we will get a value that is clearly divisible by n. There's another one of these formulas, which is n squared plus 79n plus 1601, which was discovered produces 80 primes for all the values of n from 0 up to 79. The product of its coefficients is negative 126,479. So let's look at formulas of this form. We have n squared plus an plus b, and we are limiting the ranges for a and for b to be 1000. They range from 0 to less than 1000, and the bars here mean absolute. So that means that negative values also fall in this range. So negative 40 is an equally valid value for a as is 40. The bars make it absolute, so the negative gets dropped, so they are considered to be the same for the range specified here, but we do need to test both of these values. Now, with all this description out of the way, we are finally ready to receive the actual challenge. Find the product of the coefficients a and b for the quadratic expression that produces the maximum number of primes for consecutive values of n starting with n equals 0. So Euler found the formula n squared plus n plus 41. Basically this has an a value of 1 and a b value of 41, and this produced 40 primes. And we are interested in, if we change a and b in that formula, will we get a series that is longer than those 40 primes. One example is given where b exceeds the 1000 that we are limited to, which does produce a lot more primes. Can we find something in between? Well, let's start writing code for this. So we'll hop over to PyCharm. Here we are in PyCharm, and as you can see, I've already set up the template, and as you can see, plainly copying in the description, it loses a lot of the mathematical notation we saw in the project Euler description. So here we are, we've got the boilerplate set up, and we are ready to go on at attempt number 1. We will be taking two parameters, however. We will get a upper limit for a and an upper limit for b, and which are both set to 1000, which is incorrect because this one is actually one less than this. So we need to set this up. That's not right. Let's just plug in 1000 and 1000, and run needs to accept both an a and a b, and you need to pass along an a and a b. Alright, we are on it. So we are interested in series of primes and we will be testing. In fact, we should rename these. So I'm going to copy these names from the from up here. Might as well do the same for this. Alright. So we get a specific A value. And as said, this can go all the way from negative boundary up to the boundary. And B is basically the same. We have a lower limit and an upper limit of, and we should actually add one to this, because otherwise the last element will be skipped because range. Right, and n starts out at 0, and we will get a value from our formula, which I will call f is our n squared plus a times n, which doesn't need parentheses by the way, plus b. Now, while this is prime, and now we get an interesting bit. I think we have a prime sieve method in our lib Euler, which is good for finding primes in big lists. But I think it's not very. It doesn't do a very good job at finding primes individually. So maybe we should write a function for that. And I do want to include that in our lib Euler, so I am going to import lib solutions.libeuler solutions.lib Euler as e, and I'm gonna switch over to lib Euler and add a isPrime method. So here's our sieve, and this determines prime factors based mostly on that particular sieve. But let's make an isPrime method for any given number. If n is less than 2, return false. If we get a negative number, or if we because negatives aren't considered prime, or if we get a 1 or a 0, those aren't prime. 2 might be, and if n modulo 2 no, let's hold off with that. Now we could make this use our prime factors method again, but that would call our prime sieve again, and I think that's very inefficient for this looking at one specific number. So we are going to do this a little bit differently. Alright, so let's see, we can test if this number is so if it's less than 2, or if it is equally divisible by 2, then it's clearly not a prime. 2 itself might slip through this. If n is less than 2, but it will be greater than 2, or n is equally, yeah. Right. Alright, this is basically in the theory video for Euler problem 3. I've basically discussed this method of determining if a number is prime. So yeah, here we are. This should do a pretty good job at that. I do want to test this though, so we are going to jump back over here and simply take out the definition here because it's unfinished. I don't want to do this. Instead I want to for I in range 30 print e dot is prime I, and if we run this, oh, that's not right. I do want the I itself too. Let's see now. 2 is prime, 3 is prime, 4 is not, 5 is, 7 is, 9 is not, 11 is, 13 is, 15 is not, 17 is. This seems to work just fine. Alright, so content with our is prime method. We can use it in our production code. Let's get this back. While is prime e dot is prime in this case we want to increase this series length. No, we don't. We simply want to increase n, and we want to rerun this formula here until it isn't prime anymore, and then we want to, oh hang on, we want to save more data than only this, I guess, because we want to say if n keeps n is increased every time the previous n gave us a prime. So when we look at the original formula Euler found, then this would be 0, 1, 2, 3, 4. Eventually this would be 40 and it would crash. That means we did find 40 consecutive primes. So n keeps track of the length of the stretch of primes we found. If n is greater than the longest series 0, then longest series is a new tuple consisting of n and the current a and b that we found. And we want to print out the longest series, and the actual answer is the product of the coefficients a and b. So we want to return longest series 1 times longest series 2. Alright, this should work. So let's give it a go. I'm gonna start up our main pi for problem number 27 with the default arguments 1 and 2. It gave us an answer, which, if I may spoil it, is correct. If you enter this number over at Project Euler, you will get the green check. And it's fairly efficient in only 4.29 seconds. That means that our let's compare it to our prime C function, which will be dramatic. I'm gonna copy this and make attempt number 2, and I'm slightly gonna alter that because our previous primes method did have a way of indicating if a number was prime, and that's not using this function, but that's using while e dot prime factors as a list, I guess. As I said, it's fine too. Prime factors of f, get the length of this, or in fact don't. Its first prime factor should be equal to itself. That means that this is prime. And now we are going to run this for attempt number 2, and the result will be shockingly slow, I guess. Wait, what does prime factors return? Returns. Oh, and it gets a 0, I guess, so it's an empty list. That's not cool. Alright. Oh, hang on. Misclick there. Then we do need to do this the other way around. We can have only and exactly only one prime factor in our list. It shouldn't vent. Oh right, these functions are not too happy about receiving negative numbers. Aha. So this should receive a fix. If upper is less than 1, we should simply return, I guess. Oh, I'm setting it to an absolute value here. No, this doesn't have any code to execute. This does. And it is crashing on a 0. Why does it crash on a 0? Alright. again, main pi 27. Alright, I've stopped executing. It's obvious that this takes quite a bit longer than the 4.3 seconds we had before. So we are quickly going to forget about this again. So yeah, having a primality test for just one number can help in certain situations. This is definitely one of them. But there's different ways in which we can optimize this function still, which get apparent if you take a closer look at this formula, and instead of just plugging in numbers in a loop, if you take a closer look at how this formula is constructed and see its behavior under certain circumstances, then we can make some educated guesses about what we can do to bring the number of calculations needed to get our result down further. So let's start by looking at this formula at n is 0. So if n is 0, then n squared obviously is 0 too, and a times 0 will be 0 as well, so the only thing in f at that point will be whatever is in b. B is unaffected by n being 0 leads to the rest of this formula also yielding 0, so that's a 0 plus a 0 plus b. And we are interested in primes. So at n equals 0, b needs to be prime. That means that instead of doing this, because we are not interested in negative numbers at all, negatives are not primes. Instead, we can state that b prime, a list of all the primes that can substitute for the value of b, is e.primelist, lower bound of 1, upper bound of lim b, may overshoot is false, and instead of running through this for b in b prime, let's see if this shaved off any time. Wow. That saved us 3/4 of our time, and we are now down to 1 second. That's pretty significant. And when we look at this formula and say that n is 1, let's fix n at 1. Then 1 squared is 1. A times 1 is a plus b, and this also needs to be prime. So we could say if 1 plus a plus b if this isn't prime, then we want to move on to the next iteration. Now this might help, it might not, I'm not entirely sure, but we're going to find out by running 27. And again, we've cut our time in half. So I think this is a pretty smooth solution to this problem. As you've seen, there are multiple ways to optimize for this. One is to take a very close look at how the formula works and look at the results we're interested in and how those results are reached through a given formula. And in this case, by fixing n to 0 and to 1, we've excluded a lot of cases that would be calculated otherwise and yielded no positive results. So these are now excluded before we start the heavy lifting. And we also needed to change our Euler library, and I highly advise you to take a look at my GitHub, link in the description, because we've altered a couple of things around the place, and to be completely on board with how we are doing things here, I'd recommend you to take a look at it and download it if necessary, at least check up to see if you have all the functions, and all the functions have about the same functionality in them. So that's it for problem number 27. As said, you can find the source code for this and for the glib Euler over at my GitHub, and I will see you again next time for problem 28. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.